2x, no, sorry, minus 2x to the cube. Okay, you're doing this integral. Okay, so unfortunately I don't have enough time, so probably I'll stop here so you can do the integration, right? So, okay, that is for f of x. F of y is going to be this, right? 1. So which is, yep.
So the 2x multiplied by the whole rho naught plus p naught plus rho gh, or just
Yeah, this is rho naught. So okay, sorry, rho naught. So these are separate term, right? So these are separate term. Oh, sorry, so I made a mistake here. So these are the 2x here, and the rho g 2x. No. This should be whole in bracket. Okay. Yeah. That makes sense now, right?
Is that P naught or rho naught?
That should be density. Yeah, I'm sorry.
Ooh, okay.
Oh no, wait a second.
This
This
should
is
be
not
P.
Yeah,
That's P. That's pressure.
Yeah.
Yeah, there's only one row.
My bad. Okay, now here I go.
So that's pressure, right?
Yeah, that's pure pressure.
Yeah.
Okay, now this should be now 2 another x squared still, and now this is 1, so don't worry about it. So in the x, that's it. Okay, so you do the integral. However, this integral, your x should be careful. I didn't mention this to you, yeah. So your x, okay, you're thinking about when you're looking at 0 to h, right, in y direction. You're actually integrating 0 to y, but however, you have to integrate the, with respect to x now. So for y, you're looking at 0 to h, right? But what about x? But you have to think about a relationship. Y equal x squared, right? So when y is h, your x must be square root of h, right? So your range for x must be, your domain for x must be square root x. So which means you have the integral from 0 to square root h. Yeah, okay. Forever. Same here. Okay. I think pretty much it. So I think that is the one. So I'm not sure that this is right. So maybe some plus minus signs, you be careful. But this is the way you solve, okay? In this case. Okay, now I have to move to the next problem. So I don't have enough time. So let's go to next. Okay. So this problem actually, the problem that how you apply the Bernoulli equation. Okay, so now we go here. So let's go. Okay, you have a very large reservoir there, so it's a very large tank, okay? So filled with liquid, maybe water thing, okay? Then you have open nozzle here, so basically you have a free jet later on, okay? So if you do it that way, then probably it's going to be thinner, like this. This is a free set, okay, fluid flow. Okay, now you have what is given is, okay, this is that dimension, diameter is d, okay, capital D, and you have gravity in this direction, and then you have the level, top level fluid to the nozzle is going to be h, small h. And then you have somewhere, you're interesting, this region, in pre-jet, so which is, the diameter is d, small d. Okay, and then your height from the opening to that point is going to be capital H. Okay, so that is the one. So then you have to look for. Oh, what is it look for?
Diameter at the bottom of the free jet.
Yeah, what is diameter of that? Okay, so what is D looking for? Okay, so let me go. Okay, now in this problem, actually, you actually have to start with always the assumptions of how to use when you use the Bernoulli equation. Bernoulli equation only apply when you have a steady flow and viscid. So this means there is no viscous effect on fluid. So there is no shear, nothing. And then you have the steady inviscid, and then you have what? The incompressible. Density is always constant. And then as well as streamline, okay? Along the streamlines, your Bernoulli equation always right, okay? So what is your Bernoulli equation? Bernoulli equation P plus 1 over rho U squared plus rho G Y equals constant along the streamline, okay? So now let's apply this. And then one more thing is continuity, okay? Continuity says, okay, I think probably you guys know that any, okay, so you have a linear moment, also the, what is it, continuity for this, right? dB plus rho U dot NDA, right? So usually we are considering steady, so there's no time involved here. So we are talking about this guy rho U dot NDA. Since that density, because this is since the density is always incompressible, so the density is already constant, so you can take the density out of the integral, so density is 0. Density goes away, so you only get U dot NDA. So which means if you apply this guy, okay, to here, just call a continuity equation. So these are the continuity. So continuity equations. So you're just using that. Okay. So we have two equations, Bernoulli and continuity. Yeah. Okay. So let's go there. Okay. Let me delete this guy. Show you. Anyway. So now, so you have a flow. So let's go from here. This is P naught, the pressure. Atmospheric pressure we call P naught, and everywhere is P naught, right? Because it's a jet. So even here, it's P naught and P naught, right? So now I'll consider this as my y, okay, y direction. So basically, when you have here, that means y is 0, okay? So when you have here is h, here is negative h, capital H, okay? So now let's go for applying how to apply the Bernoulli equation. So let's start from here somewhere as 1, and the flow goes here, and the power looks like that. Okay. So second point here, and third point here. They have 2 and 3. Okay, got it? Now everyone, so 1 to 2, Bernoulli equation. Let's apply Bernoulli here. Bernoulli says P1 plus rho half rho U1 square plus rho G Y1. Okay, so these are 1 to 2. Well, however, this is a very large tank, so usually we are assuming that the velocity, the top level of the fluid is close to 0. So that's why U1 is 0, close to 0, we don't care about it. So P1 goes to P naught, right? This is P naught. Now Y1 is, because we have a reference frame here, so Y at the top is going to be now H, right? So you have rho GH. Okay, got it? So then you have P2. P2 is still P naught because in the preset reason, open to there. So now you have 2 rho U2 square, right? And then rho G, Y2 is 0, right? So there is nothing here.
So that U1 gets crossed out.
Why? Because it's a very large reservoir, we assume that the U1 here, this is U1, right?
So, I mean, it does say U equals 0, so that gets crossed out, right? Because,
What do you mean?
no, it's just like, that was really right. Is that where you crossed off?
Yeah. Because U1 0, so you can take this off, right? Because rho U1 squared is gone,
Does
vanishes.
that mean the half density is also crossed out too?
So it's 0 times density, 0.
Yeah, oh, okay.
Right, so you had P naught plus Rho GH, all right, so everything's ready. So P naught gone because there's same terms in the left and right side. So then you can end being, so density as well, because this can be cancelled. So you have now U2, scalar to GH, right? Okay, from this equation, okay? So now use the 1 to 3 now point. So from the 1, we already have this guy. So P naught plus rho GH. That is P1. Okay. Now think about P3. Okay. Now P3 is you still have P naught. Well, you have rho U3 squared, right? Okay. So then you got what?
Rho G H minus H.
Now your reference rate here. So you think about this as minus H, right?
Oh, okay.
So that should be negative
Negative
capital. Negative capital H here. So okay, now P down goes 0. Okay. So manipulations you get. Okay, so you move this part here. So the second part, left hand side, then you get rho G H plus capital H, right? Is have rho U3 squared. Okay. So then you get your U3 is square root of 2 rho G H plus capital H. Right. Okay, now you have the continuity equation because you're looking for the dimension, diameter of D. Okay, so okay, now you have the. So looking at continuity here from 2 to 3. So you have U2 D. I think the dimension for here is given. Yeah, that is D there, right? So D and small d. So then if you think about continuity, so U2 times A2, which is how you calculate A area with diameter.
Pi diameter over 2 squared.
Or okay. A3 must pi
Over that.
D square over 4. Okay. So okay, now U2 must be U2A2 must be equal to U3A3, right? Since U3 is given, U2 is given, right? So you compute it using known properties, then you can actually get the output in these equations, right? I don't want to go there. So just you have this equation, that equation, three equation, you can calculate D. Okay, so just it. So I got only 15 minutes, so let me think about what we can do. Okay, let me see. Okay, let's do this. Number 1. Okay, so. Okay, now I have problems. We have a velocity vector field. U as exponential constant time, and A x squared y, x component, plus B x y squared, y component. Okay, now we have this vector field in the Cartesian coordinate. Okay, now what you're going to find is you're going to find the acceleration for this. Okay, what is acceleration? Well, before you do anything, so think about how you get the acceleration. You have to differentiate u with respect to time, but this should be material derivative. Material derivative is, that only works in the fluid mechanics. So when you have thinking about the Eulerian coordinates, Eulerian descriptions, then you're talking about material, derivatives, which is just d. You carry capital D over dt. Okay, this can be written as du dt plus, okay, u dot grad u. Okay, basically the material derivative is something like this. Whenever you have any variable, you simply plug that variable into the the parentheses. Okay, here, here, here. So basically d dt must be d dt plus u dot grad. Okay, so these are this is the material derivative. But when you have du dt, then you get a not just the the partial only. So you have additional term here. Okay. So now then you're thinking about your u now vectors. U vectors is I'll say separate as like x, y, z component. So you have a u x, u, y, u